Good morning. In this talk, I will present you the latest results from the direct dark matter searches with the CRESST-III experiment. CRESST stands for Cryogenic Irrelevant Search with Superconducting Thermometers, and it is a collaboration made of about 50 members from 8 European institutions. CRESST is located in the underground Gran Sasso National Laboratory, where the overburden of the rock provides the ideal environment to perform such a irrelevant search. In the picture on the left, you see the hut where the CRESST infrastructure is installed. The infrastructure consists of a dilution refrigerator, which hosts the detectors, and several shields are installed in order to protect the innermost part of the experiment from the environmental radiation. In the picture here on the right, you see how the detectors look like. CRESST uses the cryogenic calorimeters technology. Very simply, a cryogenic calorimeter is an absorber cooled down to cryogenic temperature, and at such a temperature so that energy deposition in the absorber, for example, a nuclear recoil due to a dark matter interaction, can be measured as a temperature variation of the absorber itself. If the absorber is also an efficient scintillator, then part of the energy is emitted as in the form of scintillation light. So the simultaneous measure of the heat in the main absorber and of the light in the light detector allow us to perform also a discrimination between different signals, so between the potential signal, nuclear recoil, and radioactive background, mainly electron gamma events. To read out such a small temperature variation, we are talking about few microkelvin, fraction of microkelvin for 100 of electron volt deposited in the absorber. We use transition edge sensor, TES, which is mainly a film of superconducting tungsten, which is operated in transition between the normal conducting phase and the superconducting phase, where we have a very strong dependence of the resistance of the film from the temperature. This allows us to measure resistance variation in the film of the order of milliohm for temperature variation of the order of millikelvin. This is how CRESST detectors look like. The main components are the phonon detector, the main absorber, which is a crystal of dimension 20 by 20 by 10 millimeter. Usually in CRESST are operated calcium tungstate crystal, but this technology is very versatile. So this crystal can be exchanged with other material, for example, sapphire, silicon, or other material, lithium aluminate, for example. The scintillation light is read out by means of a light detector, which is a silicon on sapphire of 20 by 20 by 0.4 millimeter, which is facing the main absorber. The temperature variation are read out by means of this thermometer, TES, which are structured on the surfaces of the crystal. We have a copper housing, which contains the module. The combination of a phonon detector and the light detector in CRESST is called a module. And the inner surface of the copper housing is covered with the reflective foil with the goal of maximizing the light collection. So this module is then installed in our dilution refrigerator, cooled down to cryogenic temperature, and then we perform the data analysis of our data. Basically, we record the continuous entire stream of data, and then offline we perform an optimum trigger algorithm, which allows us to optimize the signal to noise ratio and so improve the energy threshold achievable with our detector. We then perform a set of data quality cut, and we do this on a subset of data, and then we blind our analysis procedure, and only at the end of the data taking we apply our analysis chain to the entire data set. The selection criteria that we apply include a cut on the rate to select only a noise condition which are good, include cuts on the stability of the detector, so to select the detector, let's say, to reject the time periods in which the detector are not in the proper operating point. We perform cut on the data quality, so on the Palshey parameter, and on an anti-coincidence cut, so that we can reject events which are in coincidence with other detector or with the one beta, for example. And at the end, we are able to extract the final energy spectrum, which is the one that we analyze for our dark matter search. We can estimate the efficiency of this analysis chain, and to do this, we perform we create some artificial events, superimposing on some noise events, so empty baseline, which are acquired in our continuous stream. We superimpose to the empty baseline some simulated pulses that we simulate with the parameter obtained with our fit of the standard events. So at the end, we have these artificial events, and we apply our entire data analysis chain on these artificial events. And in this way, we are able to estimate the efficiency of our data analysis. You see on the plot on the right that the efficiency is about 60% after cuts over a wide energy range. And to establish the energy threshold that we can achieve with our detector, we apply a criteria that is to select the energy threshold which allows a certain number of noise events in our data. This value is 1 noise event per kilogram per day, and this corresponds for the best performing detector that was operated in the CRESST setup corresponds to 30 electron volt. This detector is referred to detector A in the following of these slides. So let's look at the data from detector A. In the plot here on the left, you see the light-field scatter plot for our dark matter data set, where you see that we can recognize and identify the different bands from electron gamma or nuclear recoils for an exposure of about 5.7 kilogram days. And the corresponding energy of these events are plotted in the plot here on the right. In this energy spectrum, we can recognize two, let's say, background lines from the cosmogenic activation of tungsten. But these lines are very important for us because they represent a sort of calibration check for our calibration function that otherwise would be very, very difficult. As you can see, we define then the region of interest, which is the highlighted yellow here in this plot, and the corresponding event in our region of interest are the one in red here in the energy spectrum. This is a logarithmic scale, so it's clear that there is a strong rise of events for energy at low energy, below few hundred of electron volt. And the origin of this, we call it excess of events, is not yet understood. So before assigning the origin of this excess to, for example, a dark matter interaction, we did some checks. The first basic check that we did was to compare this rate of detector A with the rate observed in the other modules that were operated in the experimental setup, namely detector B, E, and J. This detector at different thresholds. We go from 30 electron volt of detector A to 120 electron volt of detector B. Nevertheless, you see that in this plot where we compare the energy spectrum of these four modules, you see that the shape of these events and the rate of these events is very different among these detectors, which are of the very same type. So this is an hint that these events are not compatible with one single common origin, but the origin of this excess should be pointed to a different origin. So we then try to see what we could observe in other material, other target material. For example, we operated in the last run, run 35, that took data in basically 2019. We installed two sapphire crystal for a mass of about 16 grams with the very same housing of copper and the very same experimental setup in the Gran Sasso lab. We achieved a threshold of about 70 electron volt on the two detector, acquiring an exposure of about 1 kilogram a day. And you see that also for the sapphire in this energy spectrum, you see that the rate of the two crystal is not compatible. It's not compatible, although these detectors are in principle identical. They come from the very same ingot, the very same bigger crystal that we used already in previous run of CRESST. So this is again an hint that this origin of this excess event is not related to the material itself, but most likely comes from something related to the housing. Nevertheless, detector A, thanks to the outstanding energy threshold achieved of just 30 electron volt, allowed us to set the best exclusion limit for masses below 1.7 electron volt. This is unless until the Migdal effect is confirmed. This limit was obtained with the 1D yearly optimum interval method, combining the energy spectrum of the accepted events with the one of the expected Darmatter signal. With CRESST, thanks to the possibility to exchange the target material, we have also obtained a very interesting result on spin-dependent dark matter interaction, namely using a lithium aluminate crystal studying interaction with the lithium-7 and aluminum-27. And on the plot here, the two exclusion plot, you see the interaction cross-section on neutrons on top and on protons on the bottom, demonstrating that really the CRESST technology is has a very great potential on different physics cases. The current status is that in March last year, we started a new data taking that has to be interrupted for the pandemic, but we restarted at the end of last year and it is still ongoing. Basically, we are operating some detector with different target materials together with calcium tungstate. We have sapphire, silicon, lithium aluminate with modification to the housing to learn more about the origin of the low energy excess. We changed the holding scheme, we changed the surfaces, and the goal is to understand the origin of this low energy excess. We are collecting dark matter data, and the first look at the data is very promising in terms of the performance of our detector. Concerning the future plans, we plan to perform a major upgrade of the Gran Sasso experimental setup, increasing number of channels of almost 1 order of magnitude, reaching about 30 channels. The goal is to finalize within the end of this year the prototyping and the test of the new readout system and of the new detector. And then next year we plan to perform the upgrade of the setup in Gran Sasso and in parallel to produce and test the new detectors that will be installed, with the goal of restarting the data taking in 2023. So in summary, The cryogenic technique of CRESST is very promising, since it enables the possibility to use different material to study different and complementary physics cases, thanks to the outstanding performance in terms of low energy threshold and possibility to exchange the materials. We are currently reading the sensitivity in the field of light dark matter particle, both of independent and spin independent interaction, and we are currently performing systematic studies to understand the origin of this low energy excess, which is currently limiting our sensitivity for further improve the sensitivity on light dark matter particle. So this is a new challenge that we are facing, but at the same time, this is the new way that we have to explore new frontier and open new avenues in the field of dark matter search. Thank you.